Alright, in this talk, I'm going to give a little demonstration of the exponential form of the product of two vectors. That is, the product of two vectors is the length of the two vectors times the exponent of a unit bivector in the plane of the two vectors and the difference of the angles. This unit bivector squares to minus 1. So it behaves like a complex exponential. This combines the dot and the cross products. You're probably familiar with, well, I'll assume that everybody's familiar with the fact that the dot product of two vectors are the respective lengths times the cosine of the difference between the two angles, and the cross product is the same thing with a sine these can be combined using the fact that the product of two vectors is the dot product plus the R3 pseudoscalar times the cross product, where I is E1, E2, E3, product of three perpendicular, mutually orthonormal unit vectors in R3. And in general, the product of two vectors is A dot B plus A wedge B. So the fact that A wedge B squares to a negative number allows the exponential representation of the dot product, or of the vector product. So we have, so A wedge B squared is some number. Let's call it the magnitude of A wedge B. This magnitude happens to be the length of the parallelogram. So A, B, this is the absolute value of the area of the parallelogram is the negative square of the A wedge B. So just going to slide the board up here again. So if you call this let's call this and you can say that A wedge B divided by A wedge B is a unit bivector, and we'll call that IAB, and IAB squared is minus 1. And putting the pieces together, you can say that the product AB, and I've been lazy drawing arrows over top of everything, but if I don't do that, that's implied. So now that is A dot B plus IAB times length was trying to justify the exponential representation off the cuff, but I think I'll just, I wasn't really prepared to do that. So I'm going to just say, let's say our starting point is AB. So if we presume this is true, and this is the angle between the two vectors, let's just explore a concrete example of this. And as an example, I'm going to let's take R3 X, Y, Z, and let's draw. Let's make this A in the XZ plane of length 1. And let's also make a length 1 vector B. So here we have A equals B equals 1. And then let's look at the plane between these. So if that is 1, then this is 1 over root 2, 1 over root 2, 1 over root 2, 1 over root 2. So this one is also length 1. And let's call that C. So C going from the tip of A to the tip of B. And this is an equilateral triangle with the same angle. We've got pi by 3 in all of these angles. So now let's write out A, B, and C. So we could write A in coordinates, which is just 1 over root 2 of E1 plus E3. We're going to write B in coordinates, E2 plus E3. And C is B minus A. So that is 1 over root 2 of E2 minus E1. You see that all of these have length 1. Now, we can write these first two easily in exponential form. So when we take A, we start off with E3 and we rotate it down towards E1. So that is E3 times E to the E3 times E1 pi by 2. No, 4. And this one is E3 rotated towards E2. That is E to the E3 E2 pi by 4. Now what is this one? So there's a few different ways we can answer that. So one is we can say, let's not answer that just yet. But let's look at what AB is. So we can write product AB in coordinates, which is 1/2 of E1 plus E3 times E2 plus E3, which is 1/2 of E1 times E2, and I'm going to write E12 plus E3 times E2 plus E1 times E3 and E3 times E3, which is 1. So we have 1/2 plus a bivector. Now, if we take the length of this bivector, slide. This bivector is going to have, if we square it, we'll have length 3. So we can write this as root3 E12 plus E32 plus E13 divided by root 3. Now this is unit bifactor. Let's call this, let's call it J. So we have J squared is minus 1. And if you were to multiply this out, you'd see that fairly quickly. So what we have here is, 1/2 plus root 3 over 2 J. And that is the cos of pi by 3 plus J sine pi by 3 or exponent of J pi by 3. The other way we can look at this is using the exponential form. So we add, pen. So A was E3 times the exponent of the rotation from E3 to E1 pi by 4. B was E3 exponent rotating from E3 to E2 of pi by 4. And so we see that AB, and let's call these I, K. E3 e to the I pi by 4 times E3 e to the K pi by 4. And now I was going to mention something. So if we have a product like this, so E3 with, so if we take I E3, that was E3, 1, 3. e3 times e1 times e3, which is also e3 times e3 1 minus. So I just took e3, e1, e3. This is minus e3, e1. And so this shows that minus e3i. The bivector anti-commutes, the sign changes if the order of two factors is switched, provided the vector lies in the same plane as the bivector. So a consequence of this is that if we take e3 cos theta plus I sine theta, then that equals cos theta plus minus e3i sine theta which is e3 times cos theta minus I sine theta, and that is e3 e to the minus I theta. So if we want to change the order of a vector with an exponential when the vector lies in the same plane as the bivector that's describing the complex exponential, then we have to conjugate the complex exponential. So if we have AB as E3 I pi by 4, E3 e to the k pi by 4, and I've been kind of cavalier here, making up letters for IJK for unit bivectors. There's probably there's an IJK equivalent in quaternions for the unit bivectors. I may not have the same conventions for which is which. So if I anti-commute these, I have E3 squared times e to the minus I pi by 4 times e to the k pi by 4. And so that shows that this particular product, and I'll just let me write it out. So I was E31 and K was E32, so e to the E13 pi by 4 times e to the 32 pi by 4. We've just found that that equals e to the j pi by 3, where j was 1, 2, 3, 2, 1, 3. So we have a composition of complex exponentials in R3 leading to another complex exponential, but in this case, the angle is in the, so we started off with a rotation this way, and we had a rotation this way, and we ended up with a exponential describing the rotation in this plane. So in short, this showed that the product of two vectors, so we saw an example of how AB, what in this case was 1 times 1 times this is a concrete example of the exponential form of two vectors that happen to be length 1 lying in different planes. One was in the E3-1 plane and one was in the E3-2 plane, or that's the ZX plane and the ZY plane. That's all for now.